Hello all. As a follow-up to our first couple of lessons involving mathematical proofs, this is introducing the idea of inductive reasoning. Inductive reasoning and proof by induction are used to prove statements that involve repeating and algorithmic processes. Inductive reasoning argues from specific cases to form generalized patterns. So now that's not to say that if for some mathematical expression p, if one shows that a finite set of values holds true, that p will hold true for all cases. That's not the case at all. That's not necessarily true. If, however, one can establish some baseline of confidence in an expression p, craft the proper inductive hypothesis, and establish the inductive step, then a generalization can be made. Now, complete details on this will follow. We'll get to that. This is just an overview. However, let's begin with an example. Consider the example of summing up the first few odd integers. Let's say S1, the sum of one odd integer. We'll begin with 1. 1. S2, summing the first two odd integers. 1 plus 3 equals 4. S3, summing the first three odd integers. 1 plus 3 plus 5 equals 9. S4, summing the first four odd integers. 1 plus 3 plus 5 plus 7 equals 16. And we can continue. However, do you see a pattern? Likely you do. The pattern that should be jumping out at you is as follows. If we consider summing up the first n odd integers, 1 plus 3 plus 5 plus 7 plus ... plus the generic nth odd integer, call that 2n plus 1, this equals to n squared. Let's revisit our first four cases. One odd integer summed up is 1 squared. Two odd integers is 2 squared. Three odd integers is 3 squared and 4 squared. So this is a pretty neat thing. Now, how do we know that that will hold for all odd integers? It does. This is true. Let's name this expression, say, star, so we can refer back to it. But if I went and I considered more cases, if, say, we used more examples, we could strengthen our claim . However, this would not constitute a rigorous mathematical proof. However, it would not be an airtight argument if I were just to supply a few more examples that just happen to work. There might be something that falls through the cracks there. So there's a slick piece of logic that implies inductive reasoning that's used to write a formal mathematical proof of induction. We will review those concepts and the details, but many proofs that one writes with induction involves objects called sequences and series. So we're going to pause this lesson right now And then next time I will introduce those objects, so sequence and series, and we will pick up with those.